Okay, that's fine, Jesse. Again, if you get booted, just pop right back in, please. And there's the pair deck one last time. Okay, so we are talking about planetary motion today. Okay. Uh, the things due this week, we've got the lessons planetary orbits, revolution and rotation, and we have a show it for the Earth season lesson and checkpoint 3.3, which is going to have questions related to all of those. Okay. We are going to use mathematical or computational representations to predict the motion of orbiting objects in the solar system. Yes, Haley, thank you for letting me know. So please have your cameras on unless it's going to make it impossible for you to do the lesson and follow along. I don't want that. So I would rather your camera off and you are able to follow along than your camera on and it laggy and not understandable. So, okay, what's an orbit? Tell me what you think an orbit is or what you understand an orbit to be.
I An orbit is like when a planet follows it most of the time it's a star, but like if you're a moon, you're following another planet, and and since that central organ entity has more gravity than you kind of like follow it around in like a circle.
Okay, good. So when one object is kind of going around another object, right? Um, we use that literally and we use it figuratively when we're talking about social circles, right? Sometimes we say, so somebody is orbiting, these people are orbiting this other person. Like we talk about it, we've mentioned actors, not we, but, in society, sometimes they'll mention that some actors are orbiting another actor. So they'll show up in the same movies, but the ones orbiting are like lesser known, less famous type of thing. So, and that's more of a figurative situation. But yeah, an orbit, okay. And we've got people in here saying something that spins around something else. When a planet circles a star, it's a planet's path. Good. Okay. Yes, Evie.
I said an orbit is when a planet circles around a star, circular or ellipse.
Okay, good. So the official scientific definition is the path that a body or planet takes as it moves around another object in space. So you guys all got it, right? We'll talk about the shapes of orbits and how we predict those here today. Um, let's talk about Kepler. So Johannes Kepler lived in the 16th century, so that's the 1500s, right? So the first century was 0 to 99. The second century was 100 to 199, right? So that's why those numbers are off. So the 16th century would be 1500 to 1599. Okay, so Johannes Kepler lived in Germany. Okay, would have been called Prussia at the time. And he was a mathematician and he did a lot of observation using the naked eye, right? Just watching stuff in the sky, using telescopes that very, very rudimentary telescopes. They would have been just invented by Galileo very recently around that time, right? And he actually came up with the math, wrote down the equations that you could use to explain or to predict where these objects were going to appear in the sky. Okay? And we now call them Kepler's laws because they are laws, right? These are mathematical representations. They are an explanation of what we are seeing in real life. Okay? And all evidence and all data that we have supports them. So, Kepler's first law is the law of ellipses. And that law is that planets orbit in the shape of an ellipse, with the sun at one of the foci, or one at a focal point. Okay. Planets do not orbit stars in perfect circles. And this ultimately comes down to the fact that gravity is not a one object thing. It turns out the stars and the planets actually pull on each other. You need two objects to create gravity. Okay. Two chunks of mass to create gravity. And they pull on each other. Um, and so that's why you get these elliptical shapes instead of perfect circles. Okay. Now we do have two new vocab terms we want to introduce: perihelion and aphelion. Aphelion. Let me see how to pronounce that. You think I would know this, but I always pronunciation. Okay. Aphelion.
You got perihelion correct.
I did get perihelion correct. Thank you. So it's pronounced perihelion and aphelion. Um, we have a question. Is there anywhere in the universe where an object orbits in a perfectly circular motion? Not that we've seen. And it shouldn't happen because of the way gravity works. Um, okay. So aphelion is when the object is farthest, right? So in terms of planets, it's when it's farthest from the sun. Perihelion is when you're closest. Okay. Um, so peri means close in Greek, and Helios is the name for the Greek god of the sun. Okay. So you can see here, this is kind of an exaggerated picture, because while planets do orbit in ellipses, frequently, um, like the or rather the more unbalanced the size between the star and the planet, the more circular the orbit. So the sun is so much larger than the Earth that, yes, technically our orbit is an ellipse, but if you zoom out, it looks very circular. It looks very much like a circle. But the math for a circle, it doesn't work out. Okay. So, what's the difference between perihelion and aphelion? Perihelion and aphelion. What's the difference, guys? Tiger, you've got it backwards. Good, squirrel. Toucan, wonderful. Cat, you got it. Mhm. Elephant, yes. We need to know which is which. Good. Okay, so again, perihelion means closest to the sun. So peri prefix meaning, right? It helps to understand what prefixes mean. So peri means around or close to, right? Okay. Near, right? Okay. So perihelion is the closest point. Okay. So our second law, Kepler's second law. This one it gets really complicated very quickly, especially mathematically. But ultimately, his law states that a planet, as it moves around its orbit, will carve out an area, a pseudo triangular area here of equal area in equal times. So as a planet's going around the orbit, okay, if it takes 1 month, okay, if I were to draw a triangle from the center of the sun out, curve it around that orbit, right, and back, okay, 1 month anywhere on here is going to calculate to the same area every single time. The reality of what that means is that the planets are moving slower when they are farther away from the sun. Okay. And that makes sense when you stop and think about what's going to happen, right? So, the equation for gravity, if you think back on it, it is um, the bottom of that equation is the distance between the two objects, right? So, gravitational pull is stronger when things are closer. Okay. So, when the planet's out here in this picture on the right of the orbit, it's farther away, right? So the gravitational pull is a little bit less. Okay. Okay. And when the planet's over here in perihelion, right, it's closer to the sun, right? So the distance is less, so gravitational pull is a little bit stronger. Okay. So as this planet is moving around, that stronger, slightly stronger gravitational pull is going to cause it to move around the sun faster when it's in perihelion than when it's in aphelion. Okay. And so Kepler noticed that. He noticed that, hey, it's moving through the sky faster during, here versus here. And he was able to calculate exactly where it would end up. And so he's got some really cool equations for that. And ultimately, there's arc length and all this other stuff. But the area that is carved out here is the part that is equal in equal times. Okay, so that's his second law, that the area that's carved out in this orbit, okay, is the same for every equal period of time, whether that's a day or a month or 5 months or 52 days, it doesn't matter. Okay. So that means the planet travels that means the planet travels faster when it's closer or farther from the sun. When is it going faster? Good. Yeah. So we've got 20 people responding right now, which is about a quarter of you. And most of you are answering closer. Yes. So the planet is traveling faster when it's closer to the sun. Good. Let's look at his third law. Okay. His third law, put simply, okay, is that the farther a planet is from the sun, the longer it's going to take to orbit the sun. That makes sense, right? Like it seems kind of obvious, right? But what makes Kepler's law a law here is that it's not just common sense. He has it supported with data, observational data, and he has it supported with math, right? So he came up with the mathematical equations that describe this. Okay. We call it the law of harmonics. So you can actually calculate exactly how long a planet's year is going to be if you know how far it is from the sun. Um, as you can see, Pear Deck is starting to struggle. So it comes down to the cube of the average distance of a planet from the sun is proportional to the square of the period. So the period would be how long it takes to do that, to orbit. Adeline, you had a question.
The fact that the farther a planet is from a sun, the longer it takes to orbit It's kind of similar to how when you're running a race around a track and whoever is closest to the center of the track runs faster. Or they
So
don't run faster, but they get around faster.
yes, exactly. If you watch track race, it's one loop of the track is a shorter distance when you're closer to the center. Exactly. And that's why if you look at a track, those lines for a lap are actually staggered. They don't start at the same places. Um, in fact, let's see, running track competition. Let me see if I can show this. Show an image here. No. Okay. Top view. There we go. Okay. Oh my goodness. Why is that ringing? Hold on. I think I might have a package I have to sign for. Let me check this. I don't even know who this guy is. So, okay. But okay, so here you can see you've got the curves going around here to the right, and you see these lines here. Those represent that offset distance, right? So one would be here, and then two would be here, right? They would to travel an equal distance to this finish line. Two would have to start up here, right? Because they're you can see it here a little bit too. Um, okay, so yeah, it's you can see it in lots of different areas. But again, the equation relates the square, right? So if you take the orbital period or how long it takes to get around and square it, and then compare that with its average, the planet's average distance to the sun cubed, they're proportional. They go up the same amount. Okay. So, what are the two quantities? What are those two sides of that equation? What two things is he measuring? Okay. I'm going to pause for a second. This guy's ringing again. I don't know why. Okay. Let's see. The planets close to the orbit the fastest. Um, yes. So, Tiger, you are correct. But when we look at his math equation, what does he have on either side is what we want to look at. Yes, the distance from the sun and the time it takes to go around the sun. Good, seahorse. Good. Yes, time and distance, zebra. Good. Um, so you guys are saying semi-major axis and orbital period. Yes. Be careful. You don't want to use terms you don't know. You don't understand, right? So when you say semi-major axis, what does that mean, right? We can put it simply, much more simply, it's just the average distance from the sun, right? So average distance from the sun, time it takes to go around the sun. It is important to know those vocabulary terms, though. So semi-major axis, average distance, orbital period, the time it takes to go around. Good. Okay, now let's look at eccentricity. Eccentricity, some people might say eccentricity. Okay. It is a ratio, okay, comparing the foci, the distance from either focus, okay, to the center of that ellipse. Okay. So the way an ellipse actually works is there's two foci. Okay. Um, so as you can see here, we've got those two dots. Those are the foci. The foci is plural of focus, right? The closer to zero that ratio is, okay, the more circular it is. The closer to one that ratio is, the more elliptical. So if we look at a face, right, this one on the left would have an eccentricity of 0.2, right? The one in the middle would have an eccentricity of zero point 0.6, and the one on right would have an eccentricity of zero point 0.8, right? So that face gets more elliptical and that ratio gets closer to 1. So here, oh, great. I can't, like, it's not even showing. The pictures aren't even there. Okay, well, the pictures aren't showing up because Pear Deck sucks sometimes. Yes, exactly. The outfit got more eccentric. Oh man, that's good. I wonder if that means it's eccentricity. I've never heard it called said that way before, but okay. Man, Pear Deck is really struggling today, guys. Okay. We're not going to calculate Mercury's eccentricity because we are struggling with Pear Deck. It's giving us trouble. If oh, here we go. They're showing up. Okay. So, um, here's the eccentricity or eccentricity. Eccentricity. I gotta look up the pronunciation of that. That's gonna bug me too, guys. Eccentricity pronunciation. Oh, it is eccentricity. Man, I've been saying it wrong my whole life, guys. I don't know. I don't know. My life, my world is shattered. Okay, so it's eccentricity. Haha. Okay, but if we calculate that for Mercury, you can see that ratio comes out to 0.21. So it's very circular, right? Very circular. So here, if we were to do Earth, okay, what? That's not even the gravity isn't. Okay, we're gonna skip that. I think that equation was not changed from previous from mass and weight. We talked about orbits. Okay, what are Kepler's 3 laws? Give me Kepler's 3 laws. The first one, second one, third one. So first is on the left, second is in the middle, third is on the right. Go ahead and write those in. Okay, we did go through them kind of fast. What I would recommend, make some flashcards. Test yourself. Because some of this is understanding, some of it is memorization, right? So knowing which law is which, memorization. Understanding why it's that way is different, right? Orion, you had a question.
I have all of them. Do you want me to tell it to everyone?
Yeah, go for it.
Newton's first law is the law of eclipses. The second law is the law of equal areas.
Mm-hmm.
And the third and final law is the law of harmonious.
Yeah, the law of harmonics. Good, excellent, thank you. So the first one, the law of eccentricity, or just stating that all planets orbit in an ellipse. The second one, the law of equal areas, right? So in the same amount of time, a planet's going to carve out an area between the sun and it in its orbit that is equal. And the third one, the law of harmonics. The farther a planet is from the sun, the longer it's going to take. But specifically, the square of that of the orbital period is proportional to the cube of its average distance. Yeah. And again, it takes some of this stuff is just memorization, right? Yeah. Okay. What does a planet's eccentricity tell you about the shape of its orbit? Toucan, you got it. Owl, yes, it tells you if it's an more elliptical or more circular. Yes. Which way? It's always going to be between 0 and 1. Okay. Which way is which, guys? Is 0 more circular or is 0 more elliptical? Yes, Tiger. The higher the eccentricity, the more elliptical. Um, that's a good question. You should be able to see your animal icon like on your pear deck uh, somewhere. It's a good question. It's been a while since I've been on the student end, so I'm not 100% certain. Okay. No, that's okay. That is okay. It happens. Okay, let's talk about rotation versus revolution. This is a very important difference. Okay, what's the difference between revolution and rotation? So, this is a little video. I don't think it's going to work right now. Okay, wait, it skipped. Okay, but ultimately, revolution, okay, is spinning in place. No, sorry. Revolution is going around the orbit. Rotation is spinning in place. Okay. Yes. So rotating is rotating on the axis. Okay. So when we rotate on our axis, that determines a day, right? So rotation is day. Revolution is year. Okay. Is year. Okay. Um, I don't know. That's a good question. North Natomas. I don't know. I did not add this picture, so I couldn't tell you. Don't think that's it though. Um, okay, so it was one way to help you remember. Um, T, right? T comes before V in the alphabet, right? So rotation, okay, rotation is going to be shorter, it's sooner than revolution, right? So rotation is day, revolution is year. Okay, what about a leap year then? What's that? Well, it turns out that I'm going to skip this response. I'm sorry, guys. We're running low on time, as we always are. But it turns out that 365 days is not our exact year. It's closer to 365 and a quarter. Okay. So every 4 years, we throw an extra day into the calendar to compensate. Okay. Otherwise, we would start ending up in really weird spots on our revolution around the sun very quickly. Right. So we toss in an extra day every 4 years to compensate for the fact that the number of days it takes to revolve around the sun is not a whole number. Okay. So, yes, Adeline.
But 0.24 times 4 doesn't equal a whole.
You're right. It doesn't. And that's why every couple centuries we skip a leap year. We skip adding that day. So every 4 years we add an extra day, right? But after doing that for 100 years, well, now we have we're we've shifted where we're at in our orbit by a little bit too much. So we skip a leap year after a little while, um, and it fixes that, right? So, and none of us will ever really notice because people don't live for more than 100 years, really, right? So, I think the longest lived person ever was like 120 something. But most people die in their 90s, 80s, 90s. Okay. So, there are actually 366 days this year, guys. Wait, no, there's not. There's 200 and we're in 2025. There were 366 days last year. Sorry. I got to fix that too. Um, so length of the year is not the same for each planet because its orbital period is proportional to the average distance from the sun cubed, right? So Kepler's third law explains it. We're going to skip ahead now to Earth's seasons. Why do the seasons exist, right? Well, the seasons exist because Earth's axis is tilted. And we think it's tilted for the same reason that we have a moon. A planet that we have named Theia was about the size of Mars and it crashed into Earth. We've got the evidence from that crash, right? The moon has rocks on it that are the same as Earth rocks, and we have that crater on Earth that has rocks that are the same as moon rocks, but they're not where they are supposed to be, right? And we know Earth's axis is tilted. That's a reality. And we think that that happened when Theia crashed into Earth. Okay. And it works out. It makes sense based on where that crater is and everything. Happened a long, long, long time ago, though. Long time ago. Okay. So Theia crashed into Earth, threw it off axis a little bit, bent, so now we're like this relative to the sun. Okay. So we look here. Okay. And I meant to put a question in here for you guys that I don't think I made it in here. And because we orbit the sun and move around, rather, um, and our axis is tilted, sometimes the north is pointed towards the sun, and sometimes the north is pointed away. That's what gives us our seasons. Okay. So it's a tilt of exactly 23 and a half degrees. Okay. And that causes the sunlight to hit more or less directly. Okay. So summer in a hemisphere is when that part of the earth is pointed closer to the sun. Winter in a hemisphere is when that part of the earth is pointed farther away from the sun. Okay. So they're always opposite. Okay. Now, 23 and a half degrees is also where we have the Tropic of Cancer and the Tropic of Capricorn. Okay, so those are latitude lines that show us where that sunlight starts to become enough less direct that it's obvious to see. Okay. Okay. So the more direct the sunlight, the higher radiation, the higher the energy from the sun that lands on the earth, so the hotter it's going to be, right? It's relatively the same for the equator most of the year. Okay. But the farther you get towards where that axis is, the more that becomes less direct, a slightly different angle, right? The solstices are where um, that region is receiving the same amount of light during, like, where the day and the night balance essentially. Okay, it's where that region is getting a more direct or less direct. Words aren't working anymore. So this is referring to summer solstice and winter solstice. The day and night balancing are autumn and spring solstices. Okay. So it's the peak of those seasons. So winter solstice is when we have the longest night. Summer solstice is when we have the longest day. Okay. Oh, sorry, equinox. Equinox, not solstice. Equinox is when it's equal, right? So it's spring and fall equinox, spring and autumn equinox. Okay. And again, it says, oh, right here, it says winter solstice on the right. Well, that's winter solstice for the northern hemisphere. It's summer solstice for the southern hemisphere. Right. So think about it. Most of us have grown up here in North America, right, in California, and winter coincides with a lot of religious holidays, like Christmas, right? So, and a lot of the imagery around those has snow. Well, that makes sense to us. But if you live down in Australia, snow during those religious holidays like Christmas and Hanukkah and Kwanzaa and stuff is weird because there that happens during summer for them. It's kind of weird. They have pool parties in Australia to celebrate Hanukkah. They don't go skiing. Feels so weird, right? There's songs up here about a white Christmas again because those people lived in the northern hemisphere. There's no such thing as a white Christmas in the southern hemisphere. It can't happen unless you're really high in the mountains. Okay. Let's look at the show it really quick. Okay, so here we have, okay, Google Drawings, right? So we've got this example here in the northern hemisphere. It's autumn. In the southern hemisphere, this would be spring, right? And that happens in the months of September, October, November. Here, you are going to create these drawings to match the seasons of, ready? Summer and winter. Okay. So the way to do that, you got to double click on your drawing so that it pops up here. And then you are going to take this group of things. I've grouped it together so it moves all together, right? You're going to take this and you're going to move it to the correct spot on the orbit. Okay, so I'm going to put it here. Okay, so there's Earth, there's the sun. The sun should probably really be like there-ish. I don't know. It doesn't really matter. Okay, it's close enough. Okay, so there's Earth, there's the sun, and then I'm going to save that, right? This one, right? This one, oh, I don't want to move all of that. I just want to move this sun a little bit over. Okay. And the other season's going to be over here, right? They're going to be opposite each other because we're doing summer and winter. Those are opposites. I think that's even ish. I don't know. There we go. Okay. Save. And then, right, that's all I had to do was move it. And then I need to determine, I need to look at my lessons and the presentation and stuff. In the northern hemisphere, is this one summer or winter? and it's going to be the opposite of that in the southern hemisphere, right? And then in the northern hemisphere is this summer or winter, and then I need to identify which months that happens in. Okay. That's about all you got to do there. Okay. Questions on the show it. No, you don't have to move the sun. I move the sun because I'm OCD. Um, okay. Our exit ticket today